We can go ahead and get started. Once again, if you guys didn't sign in yet, please do so with that QR code. This is going to be probably a little bit quicker than the one that I had on Thursday was, mainly because that one was covering like two sessions because of the snow day. This one will be a little bit less math and I think maybe a bit more conceptual stuff. And then, like I said on Thursday, this upcoming Thursday, I'm going to have a quiz review past session. So it'll be like cumulative from everything this unit. But obviously, if you guys are feeling super confident, you can go in and take it on Thursday. So don't worry about going to that if you've already taken it. But for those of you who do want to wait till Friday, that'll be hopefully a good resource for you. All right, we can go straight into it. So I have some stuff from the osmotic pressure unit. To be honest, this one's kind of cumulative too. I have some concentration units, stuff like that. So this first one here, I'm asking you, at what temperature would a 0.00622 molarity solution of glucose in water exhibit an osmotic pressure of 0.15 atmospheres? Yep, the worksheet. So let me do that real quick. In your Canvas page, this is what you see when you open it up. Come over here to the sidebar that has my name on it. And then I'll always post the worksheets on this left-hand side, and then the recordings will go here once I'm done. Yep, cool. So this first one looks like a whole lot of stuff. I gave you a lot of different numbers, but really this is basic plug into a formula, get the answer. I think this is one of those formulas that you do get on your formula sheet, but um, also if you ask him, he'll always tell you. He won't like try to hide that from you. So I think you're given this formula, but it wouldn't hurt to memorize it anyways. So spend a few minutes working on this one, then I'll go over it up here. Anyone get an answer for this one? And I kind of made it tricky. I want the answer in Celsius. So that'll be your last step. Hello. All right, I'll show you my work for it up here. So again, this is using the osmotic pressure formula where we have osmotic pressure that looks like a pi symbol equals CIRT. C is the concentration. I is what is I called? Van't Hoff factor. Yep. R is your gas constant that's always provided to you. And then T is your temperature, but in Kelvin. So this is going to be a very common theme throughout the semester where you have a formula. And normally you would plug this in and solve for osmotic pressure, but it's very common that we're given this and we have to solve for something else. So This is where you have to do a little bit of algebraic rearrangement. So we're asked to find the temperature, so I would divide everything on both sides so we can isolate that variable. Does everyone feel comfortable with that? No, that's going to be the formula for when we're adding a solute to water and we're either elevating the boiling point or lowering the freezing point. That's a different one. And that one I think might also be given to you, but so whenever you see the word osmotic pressure, use this formula here. That one would be if somebody was asking, what is the temperature after adding a solute, what is the boiling point after adding a solute, or what's the freezing point after adding a solute? So yeah, if you're given osmotic pressure, that's what you're dealing with. You're going to use this one here. I rearranged it so I can solve for T. We have 0.15 already in the numerator. We can divide by our molarity because it's given to us. The Van Hoff of glucose, this is one of those things you kind of have to memorize, is 1. That's because glucose is a non-electrolyte. Um, it's C6H12O6. You don't really need to know that, but when you see a lot of these carbons and hydrogens, that's your indicator that we're dealing with a non-electrolyte. So if you drop this into water, it's going to stay as glucose. It's not going to break up into separate ions or anything like that. So Van Hoff of 1, gas constant there. We get the answer of 293.7 Kelvin, and then the last step is to go from Kelvin to Celsius. So we subtract 273.15. And this is what I got here. Anyone have any questions about that one? Sweet. All right. Next one, this is conceptual. So I want to invite one of you guys to, if you're feeling brave, speak out what you think the answer is. You might see on your test some sort of image that kind of looks like this with the word semi-permeable. When you see the word semi-permeable, that basically is an indicator that the solvent can move through here. So the liquid part can move through that barrier, but the little dots, the solute cannot. So what do we think is going to happen here if the liquid can move, but the dots cannot? Yeah. Yes, exactly. Yeah. So right now, as it's set up, we see the liquid line is about equal on both sides. There's only a couple dots here, but then a ton of dots here. Over time, if the liquid can move, it's going to end up looking more like this, where it's a bad drawing, but the liquid layer will be here. And then we're going to have more liquid on the side with higher concentration because that's going to be favoring osmotic pressure. So this is a good way of depicting what osmotic pressure means. When you have solutes, they're actually exerting a pressure force that is drawing in liquids. So this is what it would look like after some time. Cool. And you might have learned that in like bio 140 class or something like that as well. All right, this one now is a good example of what you were asking me about of when to use the other formula. So uh, I've told you that the freezing point is minus 5.95 Celsius. So we're kind of starting backwards here. And we're dealing with an aqueous solution. Again, what does aqueous mean? Water. Yep. And it has 125 grams of water. So I've given you the weight of our solvent. And I'm asking how many grams of KCl, that's a salt that we're going to be adding in. I'm asking how many grams of that were dissolved in the solution. So this is kind of a trickier one. We need to use that formula that I mentioned, or that is delta T. We're dealing with freezing point, so it's going to be delta TF equals the Van Hoff factor times the molality times the constant for freezing point. And that freezing point constant is always going to be provided to you. So spend a few minutes working on this one. If you get stuck, don't worry about it. This one's a little bit trickier. All right, yeah, this one definitely on the trickier side. Took me about 2 minutes right there. So if you can do this one, you're in a great spot. But if you kind of struggled at one point, don't worry about it. Basically, what we have to do here is work backwards with that formula that I gave you. So again, we already have been told what the new freezing point is. So that's the first step, and that's kind of an easy one to miss. But I said that the freezing point is minus 5.95 degrees Celsius. What is the freezing point normally for water? 0 degrees Celsius. So that means that we depressed the freezing point by 5.95 degrees, right? So that means that this value here has to be 5.95. So that's already a little bit of a tricky start, but we got there. And we are trying to solve for something over here. We can find the Van Hoff of KCl. So KCl breaks up into two equal ions, so it's going to be a Van Hoff of 2. Everyone feel comfortable with that part? Okay. So Van Hoff of 2, you already got the freezing constant. So now we can isolate that variable of molality. So same thing we did on this last one where we have everything except for one variable. So we need to get that variable by itself. So I divide everything over here on both sides. So we're left with 1.599 equaling our molality. Now, does somebody want to remind me what molality stands for? Mhm. Yep, exactly. Divided by kilograms of solvent. That's the big part. So we found that as our molality, which means that we can kind of use that as a unit conversion in and of itself. That's a really big thing with this unit, is being comfortable with going from molality to moles to molarity to mole fraction to mass percent, whatever it might be. So we have this written like 1.599 moles of KCl over 1 kilogram of water. And we're told the exact weight of our water, right? It says 125 grams. So if we want to get moles by itself, get rid of the denominator, we can multiply by both by the kilograms of our water. Does that part make sense? We can cancel out kilograms here and be left with only the moles of our KCl. And then the last step there is to use that molar mass that I gave you guys, grams over moles to go from moles to grams, and we get 14.9 grams. That was a lot of steps, I know. Does anyone have any questions about the work I did there? Yeah. Right here, you mean? That's a really good question. The answer is no, because the minus is indicating that we've subtracted that from 0 degrees Celsius. And that's what we do once we get this value. So the formula looks like, if I was to write that out, 0 degrees Celsius minus our delta T F got us to 5.95. So that means that this, or got us to, sorry, negative 5.95, meaning this value has to be a positive 5.95. Yeah, you're going to be subtracting something, so it will be positive, but once you subtract it from 0, you're in the negatives. Yeah. Mhm.
The second portion,
Mhm.
you did the 1.59, and then you times it by 125 kilograms, and then
Yes.
did you take that number, did you times it by the molar?
Yeah, so when I did this 1.599 times the 0.125, that got me 0.1999 moles of KCl. So then from there, my work is kind of sloppy, but I multiplied it by the molar mass. So anytime you have moles and you want to get to grams or vice versa, that's when you use the molar mass. So I gave it to you here as 74.55 grams per mole. So if we have the moles of KCl, we can also find the amount of grams by doing, again, it's like the train tracks thing from Chem 131 where we have moles here in the numerator and then moles in the denominator here. So we cancel those out. I get that I'm kind of doing it on top of one another, so it looks weird, but that ends up giving us grams. Mhm. Yeah, yeah. That's a really good question. I feel I get asked that all the time, and I don't have the greatest answer, but I always start with what I know I have. So I know I have the freezing point depression because we're told right off the bat we're at minus 5.95. So that gives me this value here. And if I have that, I know I can find the Van Hoff factor. I know I have the freezing point constant. So then I have one variable that I don't know, and that's molality. And so I think in my mind, I'm like, okay, that's a good bet. If I could find that, if I can isolate molality, then I have something else I can work with. And then I have something over kilograms of solvent, and I'm given the grams of our solvent, so I can go to moles. And I kind of work backwards like that. I don't really have a great answer for that, though. I think practice is really the best way to get comfortable with that. Okay. Next few are real quick. These are like you either know them or you don't. And hopefully these will be a couple free points on your quiz because he likes to throw in some conceptual problems like this every now and again. So, what is the name for when a solid item goes straight to a gas? The scientific name. Sublimation. Yep. So sublimation is when you have solid going straight to a gas. And what about when a gas goes straight into a solid? Deposition. Yeah. I don't have a great way of memorizing sublimation, but I like to think of deposition as like a thing has deposited out of thin air. So you have like air and then, I don't know, a block comes out of nowhere. It's deposited. So deposition. Um, that works for me. I would go through, I know there's like a little thing that he showed you, at least on the first day, but maybe a couple times that looks like this, where we have the phases on a graph like this. Do you guys know what I'm talking about? Memorize that. Memorize the terms on that. Memorize like what the triple point is, that sort of thing. He might throw in a couple problems like that on your quiz, so shouldn't be too hard to get a few points there. All right, next one. As intermolecular forces gain strength, what happens to the boiling point and also the melting point? They both increase. Yep. So intermolecular forces, again, inter means between molecules, so it's not within the same molecule. We're talking about a big bucket of a ton of molecules. These are all interacting with one another. Intermolecular forces are the forces between each one of those molecules with one another. And as you get stronger, so as you go from London dispersion forces to dipole-dipole to hydrogen bonding up to like ion-induced dipole, whatever, as you go up that hierarchy, it becomes harder to break apart those molecules. And so the amount of energy that you need to put in to go from, say, a solid to a liquid, or maybe a liquid to a gas, it increases. Does that make sense? Cool. It's another conceptual thing to make sure you're pretty comfortable with. All right, now I have a couple more. I think these are mostly math ones, and then we'll do this at the end. But next one, we're going back to what you guys did on that snow day last week. Yeah. Hmm.
For it to melt, you need a higher temperature.
Exactly. Yeah. For some reason, that one trips me up too. Melting point, it sounds weird, but think about you have ice cube. If the melting point increases, you need to add more temperature, more heat than you normally would to get it to turn to liquid. Yeah. Mhm.
Well, increase like why does it make the answers? That when you say like because it requires more energy.
That would be a good answer. It's hard to know exactly what he's going to be asking you on the quizzes, but something like that. And if you can tie it back to intermolecular forces, then you're like golden, because that's really the big thing he's trying to hit home. Mhm. Okay, cool. Calculate the concentration in molality. So we already did a molality one. So you guys should be good with that. Of an aqueous solution of calcium chloride, and I've given you the molar mass, with a mass percent of 13.2%. I don't remember if we did this one on Thursday. We might have, but it's okay. Extra practice. Good thing. you guys want to be extra thorough, if you already got this one, try to also do the mole fraction. That's some good extra practice as well. I'll do both of those up here. All right, did anyone get a molality for this one? Yep. Yep, that's what I got. So this one, we have to do that approximation step that he talked about where you have a mass percent, and anytime you have a percent, that's the same way of saying that like it's 13.2 something over 100 because we're dealing with decimals there. So when we have that, we now have a starting place. We can do some actual work here. So we have 13.2 grams of our calcium chloride. And if we use the molar mass, we can go straight to moles of our calcium chloride. That's our solute. So that's easy. We already got the numerator done. And then to get the denominator, we know we need only the kilograms of our solvent. So we don't care about the solute. We don't even care about the whole solution. We only want the solvent. And so to find that, we know that we have 100 grams of our whole solution, 13.2 grams of calcium chloride. That's our solute. And if we subtract that from 100, then we're left with only our solvent. So if we have 86.8 grams of that solvent, same way of saying 0.0868 kilograms of it. So that's all we got to do. That's our denominator, and we can get 1.37 there. Anyone have any questions about this one? Cool. All right, let's be thorough then and do also the mole fraction because you might see something like that on the test. So mole fraction numerator is the same thing. So we already got that. By the way, it sometimes is denoted as X, the mole fraction. So we already know we're starting with 0.119 moles of calcium chloride in our numerator. But now the denominator is a little bit trickier. We need to get the moles of both our solute and our solvent separately because they're going to have different molar masses, right? Water and calcium chloride cannot be converted to moles in the same step. So we know that at least we're going to need to use our solute. So we can already throw that down here as 0.119 moles of that. But we're going to also have to find the moles of our solvent. So to do that, we need the molar mass of water. It's 18.02. I didn't include it here, but we can go from 86.8 grams of water, use that molar mass, 1 mole for every 18.02 grams of it. See what that gets us. Gets me 4.82 moles of water. So we're going to add that here. Because if we have the moles of our solvent and solute, that's the moles of the entire solution. So that answer is going to be 0.0241. Everyone good with that as well? Sweet. All right, then you guys are in a good spot. Next two are going to be a little bit quicker, I think. This one is going over something that I think some people were struggling with on Friday. So that's kind of talking about the surface area to volume ratio of a reaction. So I'll read this out. We have two samples of pure calcium carbonate. They each have the same mass and are reacted separately with 1 molarity hydrochloric acid at the same temperature. One is a big, large chunk of calcium carbonate. The other is a sample that's finely powdered into calcium carbonate. And I'm asking which one do we think is going to react faster and why? The why is the more important part. First off, what do we think? The powder or the block? Powder, yeah. And how come? Mhm. Exactly. More collisions with the thing. Exactly. So as we go from one big block, the surface area is really only that outside 6 sides. But if we have a ton of little pieces, all of a sudden we have way more sides that we can deal with. So they're going to be making contact with the hydrochloric acid at a greater rate, and that's going to lead to a faster reaction. So having that down is also a good thing to know. All right, next one. I think this is the last thing I have. Um, I wrote a reaction as 2A plus 3B going to form 4C, and I'm asking what would be the reaction rate for the reactants and products. So you kind of learned a new way of talking about rates on Friday, I believe. So using those coefficients, spend a minute or two writing out what those would look like. Mhm. Um, I'll show you. This is what I picked down. So I was kind of going for this way of writing the reactions. So um, as you guys learned, reactants, and I mean, you've known this for a long time, as a reaction takes place, you're going to be losing the reactants. They're being consumed and you're forming products. That's pretty standard stuff. But we learned this new way of writing the rates of reaction. And I don't think you're going to go into a ton of detail yet on this, but the next unit after this quiz is almost all about integrated rate laws, rate order. You might learn order tomorrow. But that's for a little bit later. This is how we kind of write these. So we have the reactants are always going to get a minus in front of them because they are disappearing as the reaction takes place. There's a way you can kind of conceptualize this. I wouldn't even bother. All I would memorize is that it's always going to be 1 over that coefficient. So don't even worry about why. As long as you know it's going to be 1 over 2, 1 over 3, and 1 over 4 because of those coefficients. And then the last thing to note is that the product C is going to have a positive sign in front of it instead of a minus because we are forming it as it goes on. So not bad. Anyone have any questions about that stuff?
Didn't do like on the test video, like that formula on top of it.
I don't know how he's going to do that. I mean, obviously, he doesn't want you to do like the calculus stuff that's going on here. I don't understand that myself, but he might have you, um, he might say like which ones are being formed, which ones are being consumed, or something like that, where you have to know products versus reactants, that sort of thing. And you guys will talk about this a bit more tomorrow, and I'm guessing that's going to be more uh, like what you're going to see on the real test. But not a whole lot to worry about there yet. For this last part, we kind of already hit most of these today, but again, definitely be making sure you're doing like flashcards with this to keep this stuff fresh because I know for a fact these won't be given to you on your formula sheet. Everything else that I've said might be. Always ask him, he'll know. But this is stuff that you have to memorize. So molarity, someone want to say what the units are for molarity? Hmm. And be specific. What moles of solute? Hmm. And it's important because totally like you could be asked that and then if you think only moles over liters, you might miss one detail. So molarity is the capital M and it's moles of our solute over liters of the entire solution. Um, Molality, we already talked about that a couple times today, is moles solute again in that numerator. But then what's the denominator for that one? Kilogram solvent. Yep. And then parts by mass. This one's not that tricky, but we're dealing with mass units, so it's going to be technically it could be anything. It could be grams, kilograms, any unit of mass, but you're going to most often see it as grams of our solute over grams of the entire solution. And then mole fraction, same thing, but replace grams with moles. Moles of solute over moles of that entire solution.
What was it? Okay.
Yeah, mhm, exactly. Anyone have any questions about this stuff or anything we did today? Yeah.
I think talking about
Mhm.
that. Was
No. I'm honestly surprised he talked about that. Was that on Friday?
no,
Okay, yeah. No, you don't ever go into calculus. In fact, there's one time where you might have to use the quadratic formula, but even that he makes it so you don't need to use. So he like anything that is advanced math, he throws away for this course. So you don't need to worry about that. Mhm.
formula on the hammer thing you didn't give us.
Yeah. Yeah. He will give you a formula sheet with basically everything. It's posted. Good. Yeah, take a look at that. Anything that we've done that is not on there, definitely memorize it. You don't want to lose points that way, but he gives you a lot of formulas, and I think it's the same one that you get on the final, and the final's cumulative. So Thursday, same time, same room, so 5:30. Who are taking it that day? I don't have the recording because I make it right now, but I could maybe try to post the worksheet at least, um, to get some extra practice. But like I won't have an answer key out yet. Maybe I'll talk to Blumling, see if I can do something different because I realize that doing these on Thursdays, most of the time that'll kind of conflict. So maybe I might have some sort of answer key or something I can get out. Cool. How many people think they will take it on Thursday? Show of hands. Oh, good for you have to. That makes sense. Got it. Okay. Well, yeah, I'll try to do something like that. How many people think this is the hardest class